And thank you for turning up at my talk. I know that I'm one of the last person to be between you and the beer, so I try to be fast and get on with it. I'm going to be available in the after the talk. Uh, so I'd like to start my presentation with a quote from 19th century military strategist von Clausewitz: "Machine learning is the continuation of software engineering by other means." In our talk, we are going to see that machine learning is not that different from software engineering. We can take a lot of ideas from them. They spent 30 years on figuring out how to do code, so we can bootstrap our life by going with them. The title of the talk is Clean Architecture: How to Structure Your ML Projects to Reduce Technical Debt. We are going to look at how technical debt ruins your productivity. We are also going to look at how machine learning products gather technical debt in the first place and why they are particularly prone to do that. And we are going to look at some of the relevant software engineering concepts, just very briefly, about decoupling, refactoring, and some design patterns. There is almost going to be no machine learning in this talk, so sorry for that. About me, my background is in finance. I also spent with King Digital in Stockholm a couple of years in mobile gaming. I was head of data science at fintech, where we did industrial scale natural language processing for investment bank, and most of the content from this talk is coming from our experience there. And currently, I teach data scientists to write better code, also known as I am a startup machine learning consultant. I have a blog, please check it out, laszlo.substack.com, and we also have a community. If you like the content of this talk, please join it and take part in the conversation. This is very much a work in progress talk or concept, so it means that we really like to have other like-minded people to help us. And I'm also going to share the slides on my blog posts, so you can have a look at this. Let's first take a look at what do we mean by machine learning products. Machine learning products are not MLOps. It's important to understand the relationship that MLOps is a set of infrastructure that is helping MLOps products to get into production. And it is also not data analysis. Data analysis usually have a very short lifetime. Usually there is a stakeholder who is raising a request, and the data scientists do this analysis and then hand back this, the results of the analysis. And after that, the code or the assets are scrapped. So what is MLOps products? ML products? They are complex business processes that are describing end-to-end input-output relationships in the business. It means that they are somehow autonomous. They need to work without you interacting that, not unlike data analysis. And typically, they have a long lifespan, right? So there are models that are going to be in production for 2-3 years. So it means that if you are investing in the quality of that a short period amount of energy early on, there is going to be a long period of time when this efforts can yield. And it means that you're going to do some kind of business value by taking care of the quality of these products and the code of these products. So why does technical debt matter in ML products? ML products are usually solving fuzzy real-world business problems. There's a lot of stories about someone solving a business problem with a regex or a query. These are very, very rare. Most of the time, you are going to face business problems that have never been solved before. Unknown consequences of data quality issues that you are only going to figure out when you are in production, and also other situations. So these are inherently unspecifiable. It means that no matter how much energy you are spending on planning, you are going to find specification very late in the project, and you need to react to that and refactor your code and incorporate this knowledge, what you just gathered. It also requires constant updates. The business context changes, the environment changes, distribution drift. So it means that you need to reflect to that, go back to the beginning of the project, and then change it and refactor this to create a new product or update the existing product. Let's take a look at how the machine learning lifecycle, 5 steps in creates this technical debt and creates productivity problems. The first step is EDA, when you are dealing with the data, and then usually you deal with, in a POC, with the models. You productionize this model and test it in the A/B testing and MVP phases, and then you have some kind of continuation with business as usual, with monitoring. How does this create technical problems for you? Often, the first 2 and the latter 3 steps are done by different teams. The first 2 is by data scientists, and the next 3 is by MLOps teams. It means that there is a change in the production environment. There is some kind of unforeseen consequences, and that's where you are gathering user feedback. This needs to be handed back to the data science team, who are working on an experimental version of the product that is in production. They need to evaluate whether this kind of user feedback, how can be incorporated into the product, and then hand it back to the ML team, who will going to productionize it again and create this friction between these 2 teams. Obviously, if there is a lot of changes happening at the same time, this is a very dynamic environment. Usually these 2 solutions are very far from each other, and then you start thinking about version 2, and this is kind of like the opposite of agility, of thinking about inversions. You are going to be behind on producing business value. So let's take a look at what's technical debt, what's the definition of technical debt, and what is technical mess, because that's another concept that I would like to introduce. Lack of specification, documentation, and infrastructure is not technical debt. You just haven't wrote that. You need to get on with it, and then it's not missing features. These are also just things that haven't been done yet. And it is also not broken models. So bias, drift, regulatory requirements, ignorance is not technical debt. You haven't created a solution that reflects the specification. And it's also not bad practice. That's just technical mess, right? If you are writing code that is hard to read, or you are not testing your code, that's technical mess. Technical debt is an attempt to gain knowledge with a plan to correct it later. So you are maintaining a quality of your code at constant levels, and sometimes you are running experiments where you are allowing yourself to create situations where you can back out of it. That is what's called technical debt. And you need to maintain your code quality so you can talk about this. Ward Cunningham, so the person who created technical debt, said that paying back tech debt depends on writing code clean enough to be refactored. What does it mean? What is refactoring? Refactoring is changing your code without changing its behavior. Why would you do that? We know that everything can be written in multiple ways, and there is no reason that the first way you wrote it is the best way. So what do? You write your code, write tests around it, which checks whether its behavior is not changing. Then you are modifying the code and get into a state that is useful for you in the future, which is a better better state. And this state have quantifiable qualities. You know how you need to do it. But this requires fast testing, and it also requires experimental operational symmetry. What is experimental operational symmetry? It's a fancy name for running the same code everywhere. So you're running the same code on your laptop, you're running the same code on the testing, training, evaluation, or in production. If you have this enables refactoring. How does it enables refactoring? When you're changing your code and you are deploying it, you would like to know that the same code will not going to break production. So you must test it on your laptop, the same code that is eventually going to be in production. And this requires this concept of EOS. So then it means that the changes will going to be reflected as it is in production. This also requires decoupling to even talk about EOS. How does it work? You solve this problem by reducing the dependency between components of your system. This helps you hiding implementation details, and it also helps you the problem called cake, which is if you change anything, it changes everything. If parts of your code is not knowing about each other, then it means that changing them will not going to reflect on the other. Let's take a look at how to do that in practice. I introduced you two concepts called inversion of control and dependency injection. These are quite similar, so I have a separate slide for them. You can imagine that your own code is this blue box. So anything you do there, like training a model or creating a data set, is this blue box. This blue box doesn't know what kind of environment it is operating in. The infrastructure, if it exists, have an entry point that is calling your code and it starts running. This is what's called inversion of control. It's not your code that is calling other parts, someone else is calling it. And when it required to touch an external system like a database or an external service, it doesn't do it directly, but through an adapter. Why is it important? You can imagine that if your code in production need to send an email, and an external service, some kind of emailing service, then the blue box cannot run at all if it's connected to this emailing service, because every time you run a test, it would send someone an email. This is clearly unacceptable. So you need to somehow abstract that, and this is what you achieve with an adapter. So how does it look in a testing environment? The same code, the exact same code, runs the exact same way, but now the test setup, which is much simpler than the production infrastructure, calls your code, and instead of a database or an external service, it connects to a file system or a mock service and just records that, for example, if you need to send an email, that email would have been sent in a production environment. How does it look? A more detailed picture if you are in a clean architecture. The primary concerns of your data science effort is always some kind of business problem, and that's why that's in the center. And this is surrounded by domain-specific problem like domain models. So if you are working in a bank, accounts and clients. If you are working in some kind of e-commerce and transactions and receipts. But these all have a reflection in your domain model, and the business logic is operating on this domain model, and the models themselves are connecting into this somehow. And most of your effort as a data scientist work in this area. This is surrounded by a lower level of abstraction, which is required for the MLOps exercises or machine learning exercises, and only these are these services that are aware of the outer layer, which is the computing infrastructure, databases, and storage and external services. And you can think of this because you are decoupled from these services. You can outsource them to other teams like an MLOps team or a DevOps team or software engineers. They can take over these and help you with this. The test environment, you can replace these, just the outer layer, with mocks that are going to help you testing and running your code without the production environment. Let's take a look at 3 useful design patterns to implement this. This is pretty much implementing the same concepts of decoupling from something, which is the adapter pattern, the factory pattern, and the strategy pattern. So the adapter pattern is, you can see that the code have been refactored here. You can see that the main code is directly calling a database, which is unacceptable because obviously if you don't have this database on your laptop, you are not going to be able to create the data frame from it. So how do you solve this problem? You are wrapping this code with an external, with another class, and only this class will going to be plugged into the instantiation of the main program. And therefore, your main code and the run function will not going to know where is this data coming from. So you can swap that from, get the data from a file or anyone else, but the same code can run in production and in testing as well, or training. The factory pattern is taking this to a new level. As we speak before, you're not supposed to depend on simple data structures like a data frame, because that's not a domain-specific problem. You would like to have, for example, a customer to be present in your coding environment, and this is what you achieve with a factory pattern. And the third one is what's called a strategy pattern, which is particularly important for machine learning applications and data scientists, because we are regularly making algorithmic choices that may or may not be correct. And therefore, we would like to have a situation where we can back out and then swap these algorithms, and the strategy pattern is just for this. You can see here that, for example, this model creates a logistic regression, transforms a domain model into features, and then plug these features into the model, the main code. The problem here is that if you would like to change this code, then it means that you need to rewrite your main function. You would not have the flexibility to do this easier. So therefore, you wrap this model with a special class and then move it external to from the main code, and then just plug it in an instantiated version at the instantiation time. It also helps another feature called Coherence. You can imagine that if you have a deep model, that let's say it have a parameter called layers, and then you pass this parameter to your main function, and then the main function will going to store it in a property and then pass this property at construction time to the model, which is constructed in your code. It's very difficult to remove this and then replace it with another model, because you need to, even this simple example, you need to change your code in 5 places. So what can you do? You can wrap your model construction into its own class and pass the parameter to that class only, and therefore you can remove it from your from main class, and only the part of your code will going to know that the model has layers. That is absolutely necessary, need to know about that. That's important because, for example, if you switch instead of a deep model into a random forest, which has like trees, that's not a problem, because that version of the model class will only going to have trees, and the main code doesn't need to be changed. And these are interchangeable from that point onward. So let's take a look at how the workflow happens from scratch. So first you define your data classes. These are usually happening at the time when the business problem is defined, because these data classes are usually coming from reflecting business problems from the data science team or the business team, and then you can wrap your data sources where you are getting the information or the data with factories that are constructing these data classes. So obviously in an experimental phase you are using like file-based systems, but later you can replace these factories with implementations that are connecting to external sources or databases. You set up a test environment. As we speak about that, it's very important that you have a fast and early testing. Usually we only do like some kind of functional testing where you are testing with the real data, what you are getting. What you need to do with your code, like any kind of verbs, you use define your interfaces or something like that. Then that's where you're implementing what you actually want to do with your code. And then you collect these interfaces into service classes. So it means that you structure your code as you are writing it. You don't try to create a structure before you start implementing it. The next step is to start doing dependency injection, because obviously you are organically wrote your entire code base. So it means that it's not in the state that you think it should be, and then because you set up the test environment, you can create dependency injection, and you can experiment with your code of what's the best way to structure it, while you know that it is doing what you were intended to do at the beginning. And then when you are moving to productionization, then because your project is defined through a clean architecture, you can plug in the right external services, replacing the temporary ones in the MVP state or a POC state. Then you can set up the production environment, and when you are in production, you can take the same code, put it into your test environment, and experiment with the strategy pattern if you would like to try new solutions. So obviously everyone works with notebooks, all data scientists, and then let's take a look at how the structure helps you if you are working in this environment. You can load the data with the factories, because these are just classes, so you can just instantiate them in notebooks and then get the data. You can wrap these with data frames and then do your analysis, and then you always know that either now you are in a production code or you are doing an analysis code, because if you are touching the data frames, that's usually like that. And then you can create custom experiments by instantiating your main program, because you remember that your main program is just a class as well. So you can just create your entire thing. And this is where inversion of control helps you. And then even in your notebook, you can create experiments by implementing the strategy pattern locally. So what's the benefits of this? Good layers of abstraction. So it means that you always know what kind of mindset you need to be. So you have the analysis mindset when you are trying to figure out whether your code does something or not. You have the product mindset when you are writing code that will going to be shipped into production. And then you have the infrastructure, which is neither of that. So you can push these out. There is a high level of flexibility because of this decoupling. So you can experiment without destroying your own code. You can manage your complexity because often we face complex problems, so this requires complex solutions. So you would like to have a solution that is easy to start and then it can reach any kind of complexity, and this provides you that. And the EOS helps you high-speed iteration because you are running the same code in production and in testing. There is no friction when the machine learning team, MLE team, is translating your two solutions from one to another, and that's the source of the high-speed iteration. Right, I'm not going to read the takeaways because I'm run out of time, but I have a blog. Please subscribe to it. And there is a community that deals with code quality for data scientists, CQ4DS. Please join. Right, thank you very much for your attention.
So thank you. These patterns that you mentioned, are they described more in detail on the blog?
Yes, but usually this is almost it. All right, it's usually I think of as the less, the more.
Okay. Do we have a quick question from the audience? So then I will squeeze in one of my own actually. So you said that tech mess is bad practice. And tech debt is when you do something to gain knowledge so you can refactor it in the end. But often you realize what is a bad practice in hindsight when you've actually gained that knowledge. So the difference between tech mess and tech debt can be very hard to...
Yes, that's a very good point. So most of the problems with agile solutions and experimental situations where you are coming up with solutions as you are doing them is that a lot of problems are emergent, so you don't really worry about making wrong decisions. You are just going forward with it, and when you are realizing you have the tool set to resolve them. So I would not worry about a very clear-cut difference, but the takeaway is that you do need to practice refactoring, and then you need that list of dependencies that you need to be allow refactoring.
Okay, yeah, that's a nice perspective. One quick question. It's very quick, good.
Thank you for a great presentation. Do you have any tips for us data scientists? What could we practice next week from this talk that you gave?
I have content on my blog post, which is an open source exercise, which you can take a look where we are going through the steps of what's required to refactor a notebook into a code similar to this, and then you can find out the mechanism of that. Because that's one important takeaway is that writing good code is a craft, so you need to do it, and then you are going to get better at it, and you can take it to the next level. Thanks for your question.
Okay, so do the exercise. Okay, thank you, Laszlo.
Thank you very much again. Cheers. Thank you very much.